Good afternoon. Welcome to the APA Standards and Codes webinar series. My name is Billy Zadig, Standards and Codes Administrator for APA. Just a couple of housekeeping items before we get started. This webinar is being recorded. Recording and presentation slides will be posted to our webinar page on the APA website in a few days. All attendees are in listen-only mode. Please type your questions in the chat box and they will be answered in the order they are received during the Q&A session at the end of the presentation. If we run out of time and we still have questions, responses will be sent directly to the person asking the question. Continuing education credits are being offered for this webinar. Please contact me at billy@apa.org for more information. Also, if you have more than one person attending the session from a central location, please contact me so everyone can get credit for attending. At this time, it is my pleasure to turn this over to Mike, our presenter for today. Mike?
Thank you. Good afternoon, everyone, and good morning as well. My name is Mike Bedone, and it is truly a pleasure to be here today presenting the topic of air handling unit refurbishment for compliance with NFPA and ASHRAE. I'll start out with a bit about myself. I currently reside in Orlando, Florida, but I originate from New Jersey, where I attended Rutgers University's College of Engineering and obtained my Bachelor of Science in Mechanical Engineering. Out of school, I was hired by GE Plastics onto their Edison program, where I was trained as a plastics engineer. At GE, I focused on the application development of flame retardant plastics and plastic applications, and I've continued to do that throughout my career. Fast forwarding to 2005, I co-founded an Orlando-based nationwide company called AQUIS, where I've used what I learned with respect to developing code-compliant polymers to deliver solutions for the comprehensive refurbishment of mechanical air handling units. Which brings us to the topic of the day, mechanical air handling units. And to drive the point of the importance of focusing on mechanical air handling units, I put together a quick study looking at the top 25 universities off the US News and World Reports. We found that those top 25 universities have an average of 207 buildings per university, an average of 12.5 million square footage of air-conditioned space, which equates to approximately 17.8 million CFM of cooling required. To convert this into air handling units, we look at a typical 20,000 CFM mechanical air handling unit, and that means that each university has approximately 780 air handling units. And if we were to look at the cost of replacing those air handling units, in fact, just 10% of them, we would see that the approximate cost to replace just 10% of the air handling units is $21.3 million. Now, this does not account for the disruption caused, the significant downtime caused by air handler replacement, nor does it account for the strain on project management resources. And thus, we focus on the opportunity to refurbish mechanical air handling units. So with that, as for the agenda, the first thing I'll cover is common issues with aging air handling units. We'll move on and look at drivers for refurbishment. We'll then talk about regulatory standards that drive the refurbishment of air handlers. And then look at common refurbishment methods that are currently used in the field. We'll then look at a best-in-class solution for air handler refurbishment. We'll look at a financial justification for refurbishment. We'll look at a couple of case studies, and then we'll move on to questions and answers. So with that, I'm going to begin by sharing a few photographs of typical situations that we see in air handlers, typical failure modes. The first one we see here is a hospital in Texas that clearly has significant standing water in the condensate pan, also significant pathogenic growth, and significant corrosion of the ferrous metals. Here we see an air handling unit in New York City where the floor of the condensate pan had corroded away which exposed a flammable polystyrene foam. Here we see a university air handling unit in Michigan with clear issues with both standing water and corrosion. And from experience, we did note that this unit was contaminated with Legionella. Next, we look at another university air handler in Michigan. This one I remember distinctly because as I entered the air handling unit to conduct the assessment, my foot went through the floor. So this one I won't forget. And here's an air handling unit that was attempted to be refurbished with a commercially available two-part epoxy. You can see that the refurbishment failed in that, for one, the unit still has significant standing water and obviously significant pathogenic growth or biofilm inside the air handling unit. Also, this air handler was leaking out into a mechanical space. We see here an attempt at installing a properly configured P-trap on an air handling unit. We refer to this as our rattlesnake trap. This, as you'll learn here in a few minutes, this trap does not function properly as much as it looks interesting. And here we see a condensate pan and coil that is significantly fouled, also leading to significantly diminished performance of the coolant coil based on biofilm fouling. So with that, the common issues that we see throughout, for one, would be a lack of pitch in condensate pans or the presence of standing water, which really is the root cause of many of the issues we'll discuss. Fungal and bacterial growth, flammable coatings that were installed to remediate leaks caused by corrosion. We have destructive water leaks, rust and corrosion, compromised structure of air handlers, blocked and fouled coolant coils, and ultimately leading to a limited service life of that air handler. Now, what are the drivers that impact air handler refurbishment? What we've seen, typically, the reason customers approach us to refurbish air handlers is most often a major mechanical failure of an air handler where there's significant corrosion and damaging water leaks involved. Also, we'll see customers approaching it more proactively, looking at air handling units that show moderate signs of rust and corrosion and standing water, and look to proactively address those concerns. And at times, we also see customers refurbishing air handlers to address indoor air quality concerns. And this is particularly as it relates to fouled coolant coils. Other customer drivers are capital budget constraints. Obviously, the cost of replacing an air handling unit is exorbitant, and so often this is the most important driver. Downtime concerns. We see many cases where 6 to 8 weeks of downtime is required for the replacement of an air handler. Operations and maintenance costs, regulatory noncompliance, improved asset valuation, and lastly, energy and environmental initiatives. All are drivers for customers to replace or rather to refurbish air handling units. Now, what are the regulatory standards that drive air handling unit refurbishment? First and foremost would be fire codes and standards. There are a number of fire code standards and model codes which drive the regulations. Most notably, NFPA 101, which is the Life Safety Code, and NFPA being the National Fire Protection Association. That specifically calls out NFPA 90A, which is the code specifically for the design and installation of air handling units. Also, you have IMC, which is the International Mechanical Code, and UMC, which is the Uniform Mechanical Code. And the bottom line is that every jurisdiction in the country falls under one of these entities, and all of these standards are exactly the same as they relate to the use of non-compliant materials and coatings in air handlers. So from here forward, I'll refer to it as NFPA 90A, but it actually entails the requirements for all of these. Other standards we have are for indoor air quality, and most notably ASHRAE 62.1. ASHRAE is the American Society for Heating, Refrigeration, and Air Conditioning Engineers, and the 62.1 standard is designed to ensure proper indoor air quality within facilities. Also driving standards is OSHA, the EPA, with respect to the use of antimicrobial elements within air handling units. And then likewise, healthcare accreditation organizations like the Joint Commission, DNV, et cetera, also drive regulations. First, we'll talk about the fire code. The first thing to cover is fires in air handling units. I do often get feedback that people are surprised that the standard exists. They don't believe that fires start in air handlers. And I can tell you firsthand that fires do absolutely start in air handling units. The first case here was a hospital up in New York State where a heating element came into contact with some filter media, which ignited the filter media and caused a catastrophic fire within that air handling unit. Another case here is an industrial facility in South Carolina that was doing welding, and sparks from the welding were pulled into the intake of the air handling unit, once again igniting filter media, and once again causing a catastrophic fire within that air handling unit. Now, air handling units do contain motors and moving mechanical parts, as well as flammable media in terms of filter media. So all of the elements are there for fire within an air handling unit, and it is absolutely an issue. One of my sales directors just a few weeks ago actually witnessed a fire in an air handling unit on a routine assessment. NFPA 90A. NFPA 90A is the standard for the installation of air conditioning and ventilation systems. The standard is designed to protect life and property from fire, smoke, and gases resulting from fire, or conditions having manifestations similar to fire. More specifically, NFPA 90A states that any supplementary materials that are installed within air handling units, those materials must be tested specifically to NFPA 255 or ASTM E84. Both of those standards are the same, and they refer to testing within an apparatus called the Steiner tunnel. And when materials are tested, they must be tested at a representative thickness that they would be used in the field. Now, the specific requirements when testing to ASTM E84, the first requirement is that the maximum flame spread index is no greater than 25. The second requirement is that at the termination of this 10-minute long test, that there's no continued combustion. So essentially that the material itself is self-extinguishing. And the third requirement is that the smoke developed index is no greater than 50. Okay. Now, a few key points here. First is that you may have heard of Class A or Class 1 rated materials, and NFPA does put out classifications for Class A, Class B, and Class C, likewise as Class 1, 2, and 3. And this is different than the requirement for NFPA 90A. In fact, the requirement for Class A is a smoke developed index of 450, whereas the requirement for NFPA 90A is a smoke developed index of 50. So, in fact, the NFPA 90A for air handlers is 9 times more stringent than the otherwise most stringent classification. So if a contractor approaches you with a Class A or Class 1 coating, it likely does not meet the requirements of NFPA 90A. Another very important consideration is that when materials are tested, they must be tested at the thickness that they're applied inside the air handling unit. This is an area where some contractors try and get around the code by testing products at a much lower thickness than installed. Likewise, no other test can be conducted other than the ASTM E84 test using the NFPA 90A standard. Other fire test standards cannot be substituted. And lastly, I'd state that for any contractors that are installing coatings inside an air handling unit, the customer should be requesting a test report from an accredited testing laboratory that shows that the coating has been tested and does in fact meet the requirements of NFPA 90A. Okay, I'm going to show a quick video on the ASTM E84 protocol.
Welcome to GovMark's demonstration of the ASTM E84 Steiner Tunnel Chamber Standard Test Method for surface burning characteristics of building materials. GovMark is proud to be home of the newest state-of-the-art Steiner Tunnel Chamber in North America. Prior to testing, the test item is cut to size and mounted appropriately to mimic actual installation. The specimen is then placed in a conditioning room with regulated temperature and humidity settings. Once a constant weight is reached, the specimen is ready to test. The test specimen, measuring 24 inches wide by 24 feet long, is placed horizontally on the test chamber's inner ledges, facing down. Specimens that are not required to be mounted to a substrate are laid upon wire mesh and steel rods for support. Once the test materials are secured properly, the test chamber is closed with a watertight seal. The test material is then subjected to extreme gas flame exposure from 2 natural gas burners. A 3-inch opening near the end of the tunnel, as well as a regulated exhaust fan, allows air to be drawn through the tunnel at a steady rate, ensuring that the igniting flames are able to spread naturally across the face of the test specimen. During the test, a technician continually records flame advancement through the tunnel's observation windows, while a photometric instrumentation in the exhaust duct records the specimen's smoke developed. The 10-minute ASTM E84 test establishes the specimen's flame spread index and smoke developed are reported. During the test, the technician notes the time at which the test material ignites. The maximum flame spread distance is recorded, as well as the time at which maximum distance was reached. This determines the flame spread index.
Okay. I show this mainly to point out that this is a major fire test, and it's a large-scale fire test, and it's not easily conducted. And so, but yet it is a requirement for any material being used inside an air handling unit to be subjected to this test protocol. Okay. So with that, I'm going to move on to ASHRAE 62.1. ASHRAE 62.1 is the standard for ventilation for acceptable indoor air quality and specifies measures for new and existing buildings that are intended to provide indoor air quality that is acceptable to human occupants and that minimizes adverse health effects. Now, more specifically, ASHRAE 62.1 sets specific requirements for the design and operation of HVAC drain pans or condensate pans to ensure acceptable indoor air quality. These requirements are, first, a minimum of 1/8 inch slope, 1/8 inch per linear foot slope to the drain of the condensate pan. The drain outlet within the condensate pan needs to be at the lowest point of the drain pan and likewise the lowest point in the air handling unit. And there is a requirement for negative pressure or draw-through air handling units for a P-trap or sealing device. And we'll talk more about that. Now here's a quick schematic looking at the first 2 points. This is a condensate pan that has been, in this case, repitched. It has a slope that is greater than or equal to 1/8 inch per linear foot to the drain. and the drain is in fact the lowest point in the condensate pan. Now I'm going to take a few minutes to focus on P-trap design. And the reason is that what's really a fairly basic concept, this is an area where we see execution is often incorrect in the field, and sometimes leading to catastrophic results. So with that, we'll take a look first at a schematic of an air handling unit. So here we see an air handling unit on top of a amply sized housekeeping pad, which allows for the installation of a properly configured P-trap. Okay, this P-trap is designed with certain dimensions as specified here on the right-hand side. The most important dimension being this dimension B. Okay, so how does this work? The air handling unit would turn on, and you'd have a negative static pressure created inside the air handling unit, which would then in turn cause the coolant coils to condensate, and condensate would slowly fill the drain pan. Once the drain pan reaches the bottom level of the drain, because of the negative static pressure in the air handling unit, there would be a constant suction at the drain. And so basically, preventing water from exiting the air handling unit and exiting the drain. Now, the way that this is managed is we would compensate for it by installing a fall or a drop in the trap, such that the exit of the P-trap is below the exit of the drain in the drain pan by a certain dimension. And that dimension is B, which is equal to the static pressure of the air handling unit in inches of water column. And so, given this drop in the trap, the water can now easily flow from the condensate pan into the trap, and then from the trap into your 3-inch floor drain. This is the way traps should operate. Now, this isn't always the case, and as many of you know, it's not common to have significant housekeeping pads underneath air handling units. Often there's virtually no housekeeping pad, like in this case here. And you end up with an impossible situation in order to install a properly configured trap. So in a scenario like this, the design criteria go out the window, and you do the best you can to install a trap that allows the drainage of water. Now what happens though is that when this air handling unit is turned on, a negative static pressure is created, the coils condense, the condensate pan fills up. Now once the condensate reaches the bottom of the drain level, because of the suction in the drain, it's unable to exit the air handling unit. And the water will continue to accumulate in the air handling unit. And it actually will continue to accumulate until you achieve the proper drop-off in the trap dimension. And so now water will eventually drain out of the air handling unit and into the 3-inch floor drain, but this quantity of water will always reside inside the air handling unit. And that causes a number of issues. First and foremost would be obviously pathogenic and microbial growth in the air handling unit, a huge concern. Also, because of the moisture, you would have corrosion of ferrous metals inside the air handling unit, eventually leading to water leaks from the air handling unit. And likewise, you'd have issues with controlling humidity inside that air handling unit. Okay, I'll talk in a few minutes about one potential solution for improperly configured traps. So with that, I'm going to move on to talk about common refurbishment methods for air handling units. The first we see here is a standard 2-part epoxy used to seal an air handling unit, obviously not working based on the standing water and pathogenic growth. The issue with standard 2-part epoxies, likewise with 2-part urethanes, is that in order to work inside an air handling unit and achieve a rapid cure or setup time, you end up with significant porosity in the surface of the epoxy or the polymer, as you see here. And so these areas of porosity or bubbles tend to be sites where pathogens or debris can settle and are not easily removed. You'll also see here some micro cracking beginning to form. You can see these faint white lines where the coating is beginning to crack from below. And this is a result of poor adhesion of polymers to the substrate. So probably an improperly prepared surface. This is an air handling unit with a polyurethane coating used to seal the condensate pan. And this is a stainless steel condensate pan refurbished with an epoxy where obviously there was a failure of adhesion. The stainless steel requires an elevated level of surface prep to get good adhesion and requires the right materials. You can also see a few cigarette butts here in the condensate pan as well. This is an air handling unit that's been refurbished with EPBM film or rubber roofing membrane. And as you can see, over time, the material has in fact broken down and has begun to flake up. And these are particulates that get into the airstream and end up downstream within the facility. This is a condensate pan that had been removed and replaced with a stainless steel condensate pan, which in and of itself is not a bad idea. In this case here, it demonstrates the difficulty, though, of properly pitching condensate pans, particularly as they're reinstalled. And this air handling unit was actually pitched the wrong way and held significant standing water, which was really the root cause of their issues in the first place. Here's an air handling unit that was refurbished with a roofing tar. When that didn't work, they went back and they attempted to refurbish the same air handling unit with stainless steel sheets that were adhered to the original substrate. Okay, now we'll take a look at a best-in-class solution for air handling refurbishment. A quick overview of AQUIS. AQUIS is an integrated product development and service delivery company focused on providing code-compliant solutions for industrial and commercial air handling units. Founded back in 2004, we developed the AQUIS system, which is a patented engineered coding system for the comprehensive rehabilitation of air handlers. Since that time, AQUIS was refurbished nearly 3,000 air handling units in multiple vertical markets, most notably healthcare and higher education, but also in manufacturing, government, and commercial real estate. And as for just a few customers that AQUIS has worked with, in healthcare for UCSF Medical Center, Yale New Haven Hospital, Northwestern Memorial Hospital. For higher education, Johns Hopkins, MIT, Harvard, University of California, and Ohio State University. For the federal government, the Smithsonian, National Institutes of Health, and about a dozen different VA hospitals. And in the commercial sector, for Hershey's, Bristol Myers, Ford, and Genentech. Now, we looked before at specific failure modes in air handling units that would cause it to be refurbished. The AQUIS system, what it does specifically to address these issues. First, it has the ability to repitch condensate pans to eliminate standing water and to be compliant with ASHRAE 62.1. It incorporates an active antimicrobial surface. It's fully NFPA 98 compliant. Not only is it compliant by itself, but it can be installed over non-compliant coatings if necessary to also make that system then compliant. It's a durable, watertight system. It both seals and protects the steel or the concrete substrate. It restores structure of the air handler, and ultimately adds at least a 10-year life extension to the casing of the air handling unit. So a few before and after pictures. This is a 30,000 CFM AQUIS air handling unit with 3 to 4 inches of standing water. It was leaking into a mechanical space. Clearly issues with corrosion and with pathogenic growth inside the air handling unit. This was at a university in Florida. This air handling unit was not only pitched, but it was double pitched in that the highest point in the condensate pan was the center, and it was pitched in both directions. A new drain and trap was added on the far side of the air handling unit. Also addressed in the air handler was the coil supports, coil casings, and then the fiberglass insulation in the air handler was also refurbished and coated with a antimicrobial coating. This is an air handling unit at a hospital in Philadelphia. It had issues with the drainage of the condensate pans and also significant corrosion of the galvanized diamond plate on the fan chamber floors, and also corrosion of the inertia blocks. So in this case here, the condensate pan was addressed and repitched, and obviously addressed was the galvanized diamond plate, the inertia blocks, and the fan housings. Also the walls were addressed in this case too. And this third picture is a hospital in Michigan with concrete floors. Also, if you notice that there's perforated steel walls for the walls of the air handling units. This air handling unit was impacted by a leak in a preheat coil into this filter chamber, which was leaking through the concrete floor and into floors below. This was addressed with a self-leveled coating system, the same system, the same multi-layer system, but in this case self-leveled. It incorporated also a flashing on the walls, which prevented water from migrating through the walls and into different parts of the air handling unit. Now an overview of the solution itself. The solution is a multi-layer coating system. The base of the system is a nano clay epoxy, which provides superior bond strength to typical two-part epoxies. The epoxy both seals out moisture and air from contacting the substrate. So in the case of a steel substrate, it would prevent any further corrosion of that substrate by blocking the elements of corrosion being moisture and air. The middle layer, or the white layer, is an advanced fire barrier, which is in and of itself provides the NFPA 98 compliance to the entire system. And the top layer is a durable, waterproof polymeric top coat, which provides a smooth, hygienic surface, and is also, through its antimicrobial, abates the growth of biological agents. The entire system can be pitched at 1/4 inch per linear foot to exceed the requirements of ASHRAE 62.1. It can be utilized both in a pitched format and in a self-level format. A few details about the installation process. The AQUIS system is only installed by AQUIS's technically trained employees. AQUIS has 20 separate technicians that do nothing but travel the country and refurbish air handling units. Refurbishments are typically done in 2 separate 8-hour sessions with the ability to resume the surface of air handling units in between those 2 sessions. Prior to the refurbishment of an air handling unit, the air handler is isolated by sealing off the adjacent ductwork with visqueen and utilizing negative air machines with both HEPA and charcoal filtration. All coatings that are used as part of the process are zero VOC and have very low odors. So there are no detectable odors that are part of the installation process. And the entire installation is done in situ so that there's no need for the removal of condensate pans, coils, motors, supply fans prior to the installation of the AQUIS system. A few key details here. Typically, all coatings and subfloors or secondary condensate pans that were installed after the fact are removed prior to the installation of the AQUIS system. You can see here we're in the process of removing a coating. Parts of the air handling unit that are corroded and structurally compromised are repaired with galvanized steel prior to proceeding with the installation process. For condensate pans that are being pitched, we utilize what we call our AQUIS laser slope system, which projects a laser line at exactly 1.2 degrees, which is 1/4 inch per linear foot, so that we can precisely install to the appropriate pitch. Significant attention is paid to areas underneath the cooling coil. Most often, those are the areas that are leaking out and creating an issue within an air handler. And so that's the area we really focus on most. And for parts of the air handling unit that require slip resistance, we have the ability to install a silica into our top coat, which provides traction when walking on the surface. In terms of the overall benefits, first and foremost would be the ability to extend the life of a mechanical air handling unit and push off the high cost of replacement. As we discussed, the cost of replacing air handling units can be exorbitant. This allows our customers to delay that cost, and then likewise to avoid the disruption that's associated with air handler replacement. The second benefit would be halting damaging water leaks. When we refurbish air handling units, we do guarantee that they'll be leak-free when we're done, and if not, we come back out and address it. This obviously eliminates the fear of damaging water leaks that might cause significant damage, mold contamination, or operational disruption. The system can also eliminate standing water, which stops the formations of biofilms inside the condensate pan, which contain pathogenic agents such as Stachybotrys, Staph, and Legionella. And lastly is the benefit of peace of mind of full regulatory compliance with NFPA, ASHRAE, so on and so forth. I'm going to move on now to a financial justification for refurbishment. We'll take a look at a case study, which is of a hospital in New York City that had 52 total air handling units that needed to be addressed. They decided to do them 4 at a time, and they received a price of $800,000 to replace those 4 air handling units. At that point, they approached us, asked us if we would provide them with a proposal for instead of refurbishing those same 4 air handling units. We offered the ability to refurbish those 4 air handling units comprehensively, the interior of the air handler, and provide a 10-year extended warranty at a cost of $79,200. This analysis will look at both the impact of energy savings as well as maintenance savings, and for both the replacement and refurbishment scenarios. There were several assumptions that we made in the process. Just to point out a few of them, the energy savings of the new air handling unit was based on a 10 percentage point increase in efficiency of a 50 horsepower motor operating 8,000 hours annually at a 75% load. The energy cost utilized was 10 cents per kilowatt hour. And the ROI calculations are based on a cost of capital of 8%. So with that, first we look at the 7-year cash flow analysis of an air handling unit replacement. You see in year 1, there's no impact. Year 2, the air handler is replaced at the expense of $800,000. I should say 4 air handlers are replaced. Year 3 through 7, there's a fairly generous savings based primarily on energy savings year over year based on the improved efficiency of the new air handling unit. In scenario B, we look strictly at the AQUIS installation or the refurbishment of those 4 air handling units, which is done in year 1 at the expense of $79,200. We see a nominal year-over-year savings between year 2 and year 7 as a result not of energy savings, but of maintenance savings. Now, to compare the impact of refurbishing versus replacing the air handling unit, we compare these 2 cash flows. And we see that at the end of 7 years, there's a total of $538,000 in savings based on the refurbishment of the air handling unit. Based on that, we calculate a net present value of the investment of $489,000 and a return on investment of 667%. Now, one of the obvious elements missing from this analysis is that nothing else was done in the air handling unit aside from the refurbishment of the casing. What we find from working with general contractors and mechanical contractors is that generally the cost of replacing coils, blowers, even an upgrade to like a fan wall technology, and controls typically would fall in the range of about 35 to 40% of replacing the air handling unit. And so still providing a good return on investment if all of those refurbishment activities are being accomplished. So whether you're just addressing the casing or addressing the entire air handling unit, all of the components, still a sound investment. With that, I'm going to move on to a solution case study. We look again at the same 30,000 CFM McQuay air handling unit that we saw earlier. And based on the standing water inside the air handling unit, we decided to address the condensate pan of the air handling unit with our CPR1 pitch solution, which double pitches the condensate pan. Now, the way that's accomplished, this view here is a view as if you're looking at the face of the coolant coil. This is the condensate pan below the coolant coil. And you can see we would first install an aluminum angle to the floor, which would allow us to have a divider to generate the double pitch inside the air handling unit. On one side, we utilize the existing drain, but change out to a new properly configured trap. On the opposite side, we install a new drain and a properly configured trap. This view here now is of the cross-section of the coolant coil. And you can see that likewise, we are pitching the condensate pan in all directions. So we're pitching out from underneath the coolant coil and likewise from the upstream end of the condensate pan, essentially creating a inverted roof geometry in the floor of the condensate pan. As for the trap, this was a solution that I mentioned earlier when you don't have sufficient space outside of an air handling unit for a properly configured trap. We would utilize what we call our concentric trap. What it is exactly is 2 separate concentric copper pipes that are welded together. And you can see here how it functions. We go back to our standard air handling unit drawing. Okay. And then the concentric trap itself installs inside a standard 3-inch floor drain. And so the outside concentric pipe is 2 inches, and then the inner pipe is 1.5 inches. And the way it functions is that when the air handling unit turns on, and now the pitched condensate pan fills up, the condensate water will drain down out of the air handling unit and down into the center of the concentric trap. Okay. Now, because our drop-off or height B is met by this trap, the water then rises up inside the base of the concentric trap and then out through the holes in the outside copper pipe. And so this allows for a properly configured trap inside a 3-inch floor drain, which basically means that anywhere that you have a 3-inch floor drain, you can now have a properly configured trap to help the proper drainage from the air handling unit. Here's a picture of that same concentric trap outside of the air handling unit. Okay, and then once again, the before and the after. Okay, one last thing that I'd like to touch on briefly is the restoration of cooling coils. As part of refurbishing air handling units, coils are obviously a concern as well. Okay, now the real enemy to cooling coils is biofilm. And biofilms are complex communities of microbes and pathogens which grow inside cooling coils and prevent their proper operation. Inside coils, biofilms are have slimy, tacky surfaces, and they grab and hold on to particulates that are passing through the airstream, and that biofilm continues to grow. Biofilms in cooling coils are the source of many IAQ issues, including odors, irritants, and the potential spread of pathogenic agents. And the worst part is that over time, this buildup of biofilm will block the effective heat transfer through the cooling coil, as well as impede airflow through the coil. So first we see here a schematic of a fouled cooling coil, and you can see based on the cross-section that there's significant surface area for the biofilm to grow on. Now the issue with typical coil cleaning technologies, such as the use of pressure washers or steam, likewise the use of typical coil cleaning chemicals, such as your acids and bases, is that they fail to penetrate deep within the coil, and the only part of the coil receiving the benefits is the outer 2 or 3 inches of the coil. AQUIS does have what we call our AQUIS coil restoration process, which combines a high-performance sanitization process along with a unique probiotic technology for dislodging biofilms to completely clean coils and clean at a microscopic level, which in essence allows you to unlock the like-new performance of the cooling coil. So this is a solution that is a definite potential add-on to any refurbishment of an air handling unit. And with that, I think my time is up. I'm going to move on to some questions and answers.
Sure. Hi, Mike. We did have a few questions. In particular, one question was, does AQUIS work with AHU manufacturers to provide protective coatings on new units straight from the factory? I know we get that question often.
We do. We do often engage with the new equipment manufacturers. We've worked with Trane, Johnson Controls, and we have at times provided refurbishment services on new air handling units. Typically, though, it's once the air handling units have already been installed. And because this system is providing a waterproof seal, it's really important that it's done after it's been installed in the facility. The concern would be that if it was installed at a production location that through transport and installation, it could in fact compromise the coatings. And so on the several projects that we've done on new air handling units, in every case, they've always been done on air handling units once they've been installed, and actually not working through the equipment provider, typically working directly with the end customer or through a general contractor.
Great. One other question we got, which is also a common question: what does our system look like in 10 years, taking into consideration the 10-year life extension that we indicate?
No, that's a great question. Well, we have been doing this now for 13 years, so we do have the benefit of going back and looking at previous installations that are over 10 years old. What we find is that, for the most part, the end result is virtually unchanged. I could actually even quickly pull up some pictures here of some 10-year-old air handling units, but the top coat, the polyurea, does tend to discolor slightly over time. If there's rust coming off the coil, you might see a slight tinge of that showing up in the top coat, but otherwise it looks the same way that it does the day that it was installed. We've also found that we've seen very few field failures, even over 3,000 installations. A very insignificant number of failures to the coating itself that would impact the performance.
Great. Are there any applications? Oh.
Yeah, you know what? Go ahead and ask, and I'm gonna pull up a picture of a 10-year-old air handler in the meantime.
Oh, okay. One other question was: are there applications where AQUIS cannot be used?
Okay, I'll get to that in 1 second. Okay. Here's an air handling unit that was refurbished up in Michigan. This picture was taken the day that it was refurbished. Okay. This picture was taken after 3 years. And you can see that indications of some slight discoloration of the surface. And then this is a picture that was taken after 9 years. So for all practical purposes, it looks the same as it did the day that it was installed. And still performing as it should. This was a pitch surface that was, designed to eliminate standing water. Okay. And what was that last question, Christine? Hey, Christine?
Yep. Sorry, Mike.
What was the last question?
Yeah, the last question, and we're getting quite a few here. Let me see. It was, are there situations where AQUIS cannot be used, applications where AQUIS cannot be used?
Okay. Probably the easier thing to do would be to tell you when AQUIS should be used. And this is a good chart that speaks to that. For modular air handling units that are 12,000 CFM and larger, that have issues with standing water, rust, corrosion, water leaks, it's a great application. If it's an air handling unit smaller than that, I'd say it's questionable, and particularly if it's a DX unit and not a chilled water unit, even more likely that it would not be a good fit. Built-up style air handling units, really of any size, that have concrete or steel floors. Any floor surface, whether it's galvanized, cold rolled, stainless, concrete, that has a requirement to meet NFPA 90A, meaning that that surface falls within the airstream of the HVAC system. So this would now include air intakes, ductwork, plenums, what have you. If there's a requirement to add a coating and to meet NFPA 90A, we would be an appropriate solution there. And then lastly, any surfaces where non-compliant coatings have been installed, whether they're epoxies, tar, roofing membrane, foam, and you're looking to remediate that non-compliance, this would be a good solution for then addressing that. Okay, so to answer your question, probably really air handlers that are smaller than 12,000 CFM, or air handlers that are DX units, particularly small DX units, are not good solutions or targets for this solution. Okay, Christine, what's next?
Sure. Any difficulties with the concentric trap getting clogged with biological matter? If so, how are they cleaned?
Yeah, great question. We've actually improved the design over time. In the beginning, we actually had a screw-off cap on the base of the concentric trap, which seemed like it never really got utilized. So we ended up simplifying it and actually welding the cap on. And we have instead gone to a solution where through couplings in the air handling unit, the entire assembly can be easily removed. The cap can be screwed off on top, and you would simply flood the concentric trap with water to eliminate any debris or biological growth inside the concentric trap. And then you just put the cap back on, reattach the coupling, and you're good to go. So we have not had an issue with that.
Great. We've had a couple of people ask if we're available in Canada.
We are available in Canada. That said, we have a number of projects we've quoted. We have not yet completed our first project in Canada, but we've done a lot of work awfully close to Canada. So, we have already worked through the process of how we would work in Canada. We're just waiting for the first project to come up, and but we are prepared to do it, and we can in fact work there.
Great. A couple more since we have a couple minutes. We did get 2 or 3 questions with regard to cooling towers, and if we address those.
Yeah, great question. We do not currently address cooling towers with what we do. Part of the reason is that the requirement for chemical resistance of coatings that are used in cooling towers is obviously far and above what is used inside the condensate pans. Likewise, with cooling towers being designed to hold water, cooling towers see a lot more strain than condensate pans, and so it requires coatings with significantly more elongation than what we would use for a condensate pan. So we've looked at the market. It's because there is not a compliance aspect to cooling towers, there are probably a number of different coatings out there that could be used. Because we do focus on code compliant solutions, especially with our air handler solution, we have not gone after cooling towers. I would say though, if you are looking for a potential coating to be used, feel free to reach out to me. I could probably recommend 1 or 2 different coatings that you could look at.
Thanks, Mike. How would you say we compare with other systems in a best value bid situation?
I didn't mention it earlier, but the solution that we offer is the only polymeric solution of its type that is compliant with the fire code, and we do that through our 3-layer system, which is a patented process. We've yet to see another system which of a 2-part epoxy, 2-part urethane, any type of polymeric system like that does comply with the fire code. So because of that, we are typically sole sourced in the projects that we're in. That being said, how do we compare? The system that we've put together is very robust, and so it's installed at approximately 1/4 inch thick, except where we're actually repitching surfaces where it's actually thicker than that. And it provides a long life performance inside the air handling unit. Coupling that with the fire code compliance, the ASHRAE compliance by repitching condensate pans, which is also unique to AQUIS. I think we very favorably compare to other potential vendors of refurbishment solutions. Does that answer the question?
Thanks, Mike.
Yeah.
Any other questions that we received that were not answered? We will reach out to you directly and answer your question. Thank you very much.
Thank you, everyone.
Okay, at this time, it's the top of the hour. I want to thank our presenters, Mike, for his time. I want to thank everyone for taking time out of their busy schedule to listen to our webinar. We look forward to seeing you at our next presentation. Thank you very much and have a great afternoon.